Hey guys, welcome to my first online lecture, Topology. This course is for everyone with an interest in higher mathematics and can of course also be used as an addition to your uni courses. I'll try to explain everything in a way that everyone should technically be able to understand the content of this course, but of course that might be too ambitious, but I'll still try my best. Although topology is probably not a good beginner's course to start with. So let's get started right away. In the first chapters, probably like the first 4 or 5 videos, we'll introduce some basic terms and maybe do some recap of stuff that is mandatory to follow this course. So let's hop right in. Chapter 1. Basic terms and concepts. 1.0. First, we try to answer the question, what is topology? Let me read you a quick definition. Topology is the branch of mathematics concerned with the most fundamental notion of shape. Instead of measuring distance or angles, topology asks which properties of an object remain unchanged under continuous deformations such as stretching, bending, or twisting. At its core, topology studies continuity and closeness. It provides a framework for talking about limits, convergence, and neighborhoods without relying on precise numerical distances. This makes topology more general than geometry and analysis. Many structures studied in mathematics can be understood once an appropriate topology is defined on them. Because of this level of abstraction, topology appears throughout modern mathematics, from analysis and algebra to dynamical systems and theoretical physics. Okay, that was our short definition. Let's start with our first definition. Metrics and metrical spaces. 1.1. Let X be a set. A function d from x cross x to the real numbers is called a metric if d of x and y is greater or equal to 0 and d of x and y is equal to 0 if and only if x is equal to y for all x and y element of x. We call this property positive definity. Second, d of x and y is equal to d of y and x for all x and y element of x. We call that property symmetry. Thirdly, we're asking for d of x and y plus d of y and z to be greater or equal to d of x and z. We call that the triangle inequality. So basically what that means is that going directly from point x to z is a shorter distance than going from x to y and then from y to z. We call the pair xd a metrical space. Okay, let's look at some examples. 1.2 examples. First, the pair of the real numbers and the function d from r cross r to the real numbers, where d of x at epsilon is equal to square root of x minus y squared, is a metrical space. We call this metric the Euclidean metric. So this basically just measures the distance between 2 points, like you can see here. The distance of 3 and 4 is 3 minus 4, which is minus 1. And then you square it and take the square root, which basically just removes the minus, which is 1. And the distance here is 1. The second example is the pair xd, where x is an arbitrary set and the function d from x cross x to the real numbers, with d of x and epsilon is equal to 1 if x is not equal to epsilon and 0 if x is equal to epsilon. This metric basically just measures if 2 points are equal. It will have an output of 1 if the 2 points are not equal, and it will have an output of 0 if the 2 points are equal. Let's look at why d is a metric. This is kind of trivial, but still we're gonna do it just because this is the first video and the start of the course and not everyone might be familiar with how we do things here. So let's just do this for now, although it's not too difficult. Let x, y, and z be arbitrary elements of x. So what do we have to show? Well, we have to show these 3 points. If these 3 points are true for d, then that means d is a metric and xd is a metrical space. So this is what we have to show. So we start with 1. Per definition of the function, d of x and epsilon can only take the values 0 and 1. So the first point is basically true just by definition of the function. Point 2. In point 2, we look at 2 cases. For case 1, x is equal to y, then d of x and y is equal to 0, and of course d of y and x is equal to 0 as well. And case 2 is basically exactly the same. x is not equal to y, that means d of x and y is equal to 1, and of course d of y and x is equal to 1 as well. So the second point is basically trivial as well. So basically the only point where we have to do some thinking is the third point. So that is the triangular inequality. So let's look at that. We'll have to look at two cases again. Case 1, x is not equal to z, then d of x and z is equal to 1, because they're not equal by definition of the function. But then, if this is true, then either d of x and y is equal to 1, or d of y and z is equal to 1. And this is an and or. This is not an excluding or. They can both be 1. But at least one of them has to be 1, because if d of x and y is equal to 0, then x is equal to y, which means d of y and z is equal to d of x and z, which is 1. And if d of y and z is 0, then y is equal to z, which means d of x and y is equal to d of x and z, which again is 1. So what that means is if d of x and y is equal to 0, then d of y and z is equal to 1. And if d of y and z is equal to 0, then d of x and y is equal to 1. So one of the two is always going to be 1. So from that we can conclude that d of x and y plus d of y and z is greater or equal to 1, which we wanted to show for point 3. Case 2, x is equal to z, that means d of x and z is 0, which makes it kind of trivial because d of x and y is greater or equal to 0, plus d of y and z is greater or equal to 0. So if you add these two together, it's still greater or equal to 0. So this is true trivially. So now that we've shown that all 3 points are true, we can say that D is a metric. And we're done with the proof. So that's it for this first video, for the first part of topology. The next part we will talk about continuous functions. Thanks for listening. See you in the next video.